So for the example at the top of page 72, we are asked to use a right-hand Riemann sum with 3 subintervals of equal length to approximate the definite integral of x cubed minus 3x from 1 to 7. So our goal is to work these examples without using a graphing device, but I think to understand what we're doing, it'll be really helpful to also look at the graph. So let's start off with, like my strategy here is to always start off with a table. And so if I consider my interval that I'm considering is from 1 to 7, if we're told that we have 3 subintervals, we said that n equals 3, where n represents the number of subintervals. And then if they are of equal length, that won't always happen, but if these subintervals are of equal length, then we actually have a little formula that we could use to find the length of each subinterval. So for our definite integral, remember our lower bound is represented with a, our upper bound with b, and then that's our function inside. So if our subintervals are of equal length, then we could say that our delta x, the length of our subinterval, is going to be equal to b minus a over n. So for this problem, our delta x, or the length of our subinterval, is 7 minus 1 over 3, which is 6 over 3, so our delta x is 2. So what I would first do to solve this problem is I would make a table. It doesn't matter if you make it horizontally or vertically, but there's a reason that I make the tables for these horizontally, and we can kind of see why in just a second. Okay, even though this function isn't named, I'm just going to call it f of x for ease of reference. And so if I consider from 1 to 7, I'm going to fill in all of the x values from 1 to 7 in my table. So 1, 2, 3, and so on. Okay, now I'm not going to fill in all of the f of x values yet because we won't need them all. So if our subintervals that we're using for this problem, we said have a length of 2, I'm going to always start my Riemann sum rectangle at the a value. So the first rectangle starts at 1, and 1 plus 2 is 3. So then my second rectangle is going to start at 3. 3 plus 2 is 5. And then my third rectangle starts at 5. 5 plus 2 equals 7. So up at the top, I could just check my delta x is 2 here, here, and here. Because we increased from the left boundary, we increased by 2 to get to the right boundary for each rectangle. Going back to the prompt, we are using a right-hand Riemann sum here. So that means that my rectangles are going to touch the curve or touch the graph on the right-hand side. So that means I need to use, for my first rectangle, that has x equals 1 and x equals 3 as the sides, I need to use the 3. So I'm going to have to figure out f of 3. For my next rectangle that has the left boundary at 3, the right boundary at 5, I need to use the 5, the right-hand boundary. And then for my last rectangle, boundaries at 5 and 7, x equals 5 and 7, I need to use the 7. So by drawing a little table like this and kind of sketching our rectangles on top of the table, we can make sure that we are choosing the correct subintervals, we can make sure the length is correct, and we can visualize the right-hand side of each rectangle. Okay, so to fill out my table, we need to know f of 3. So 3 cubed minus 3 times 3, which is what? 27 minus 9. So we get what? 18. For f of 5, we have 5 cubed minus 3 times 5. So 125 minus 15. And that is 110. And then lastly, for f of 7, we have 7 cubed minus 3 times 7, which is 343 minus 21. And let's see, that gives us 343 minus 21. I'm doing this off screen in a calculator. Guys, now I can't subtract in my head. 322. Okay, so when we calculate our Riemann sum now, we are approximating this definite integral. So unlike our geometric examples, this is an approximation. And when we write our information for the sum, we have to show a product and a sum. So I'll show you what I mean. Okay, so we're going to add the area of these 3 rectangles. So my delta x, the width of my subinterval, is the width of the rectangle. And my f of 3, f of 5, and f of 7 are the heights. So we could first write this in, if you wanted to, as like f of 3 times 2, because our delta x is 2, plus f of 5 times 2 plus f of 7 times 2. We can't substitute in the delta x unless we say out like in the top delta x equals 2. But somewhere we should show the work that we are actually multiplying 18 times 2 plus 110 times 2 plus 322 times 2. And if we just complete that, that should be 900. Okay, so the approximation of our definite integral is 900. So real fast, out to the side, I went ahead and graphed this in Desmos because I think it's easier to make the table for the sum when we understand what the graph looks like. So this is our graph, f of x equals x cubed minus 3x. So to visualize the rectangles, we said first of all, from 1 to 7, we were going to break this up into 3 subintervals of equal length. So I can see that we've broken this up into 3 subintervals that are 2 units wide. And so my first rectangle, because we said it's a right-hand sum, my first rectangle is as tall as f of 3 and then goes across and then comes back down. So when we calculate that area, that was 18 times 2. That's what we're getting here for this rectangle. It's 18 is the height and 2 is the width. Obviously, the x and y axis are not at all using the same scale. So 18 times 2 is giving us the area of this rectangle. And again, what makes it right hand is that it's the right hand side that's touching the curve. So then our next one was f of 5. So this is our next rectangle. And we said f of 5 was 110. So when we find the area of that rectangle, that's 110, the height of the rectangle, times 2, the width. And then that very last one from our table is f of 7 times 2. Whoops, that's a terrible looking rectangle. So f of 7 times 2, again, we said f of 7 was what did we say, 322, I think. So the area of this rectangle is 322 times 2. And then we're just adding those areas together. And again, we can see that this isn't a great estimate for the area under the curve since all those rectangles are taller than the curve, but it's an approximation. All right, in the next example, again, we're going to try to do this without a graph, but I think it might help to go back to the graph to look at it. So use a trapezoidal approximation with 4 subintervals of equal length to approximate the definite integral of x e to the x from 1 to 5. Is this an over or underestimate of the actual value? So let's answer that question before we look at the graph. So recall that the area of a trapezoid is, again, we could say 1/2 base 1 plus base 2 times h, but I think of it as the average of the bases. And when you were in middle school math, you maybe learned to derive this formula by taking a trapezoid and turning into a rectangle. And you take some from the long base, give it to the short base, and then it's a rectangle. So when we are talking about our trapezoidal sum, it's really important to remember that the trapezoid, that the bases are the 2 parallel sides. So the bases are going to be like f of 1 or f of 5, for instance. That the height of our trapezoid, the height, that's actually going to be our delta x. And then our bases are going to be like f of 1 or f of 5. So when you're looking at those examples on the previous page, hopefully you could see that trapezoid formula in that example. Okay, so again, I'm always going to make a table. I'm showing you the graph in these videos so that we can understand what we're doing better. But so far, these are all problems that we would not use a calculator for, so we need a table. We said we have 4 subintervals, so that means our n equals 4. And again, we're told that they're going to be subintervals of equal length, which won't always be the case, but it is today. So if I use my little formula, b minus a over n, that gives me delta x. That's going to be 5 minus 1 over 4 gives me delta x, and delta x is 1. Okay, so as I make my table, I'm going to leave some space on top to like write some stuff on top of it. I'm going to call this function g, just for fun, since the last one was called f. It doesn't take much for me to have fun. I'm going to call it g. And again, I'm not going to just I'm going to start with filling in all of the numbers from 1 to 5. And the only time I would include like fractions, for example, is if my delta x were less than 1. So since it's 1, I'm just going to fill in from 1 to 5. So 1, 2, 3, 4, 5. Okay, so before we worry about filling in g, I'm not even worried about the function yet. I want to understand by thinking about my table and by thinking about this trapezoidal approximation, I want to understand what information I need in the table. So when we do the trapezoidal approximation, because we need both bases, we need both sides, the left-hand side and the right-hand side of the trapezoid, unlike the Riemann sum. So our first trapezoid is going to start at 1, and the delta x is 1. So 1 plus 1 is 2. So that's my first trapezoid. My second trapezoid starts at 2. We can't skip over to 3. They have to be touching trapezoids. So starting at 2 plus delta x, so plus 1 brings me to 3. And then from 3 plus 1 to 4. And then from 4 plus 1 to 5. So as I double check, I should have 4 subintervals. They should be equal length, so they're all 1 unit long. And I shouldn't end up short of 5. That should take me from 1 to 5. Okay, so the bummer is that we got to fill out the whole table, but at least we know for sure. Okay, so our function is x e to the x. So out to the side, I'm just gonna think about that. So if g of x is x e to the x, this is actually pretty easy to fill out. G of 1 then is just 1e to the 1. So just 1e or just e. G of 2 is 2e to the second power, so 2e squared. G of 3, 3e cubed, and so on. Okay, so we have our table filled out. So now when we go to approximate our Riemann sum, our trapezoidal Riemann sum, I know that it's an approximation, so I'm gonna try to remember to use my approximately equal to symbol. And then remember that the area of the trapezoid is gonna be the average of the base, either add them and divide by 2 or add them and multiply by 1/2 times the height. And again, our height is our delta x. So these are all bases. So like for my first trapezoid, e is base 1 and 2e squared is base 2. Okay, so we're gonna have, I'm gonna pull the 1/2 out in front. So 1/2 times e plus 2e squared. So that's the average of the two bases. And then times the height, I'm gonna write times 1. All right, as we move on to our next trapezoid, what was base 2 of the last trapezoid is base 1 of the next trapezoid. So you'll notice in the trapezoidal sum, each side gets used twice in a row. All right, so we've got 1/2 2e squared plus base 2, 3e cubed. Okay, so again, what was base 2 of the last trapezoid is base 1 now. We'll get to the point where we don't have to label these all. All right, so 3e cubed plus 4e to the 4th. And then my last trapezoid. Oh, I forgot the 1/2 on that last one. Yikes. And you know what? I forgot to write the 1 on both, and we really should be careful. Even though it's a 1, I think it's good in our notes so that we can see like what happened to delta x. Oh yeah, delta x is just 1. Okay, so last one. Like this is a stream of consciousness. Sorry that you have to listen to me talk to myself. All right, 1/2 4e to the 4th plus 5e to the 5th times 1. All right, so when we are showing our work for an AP problem, like the reader should be able to tell that this is the area of a trapezoid. That's why I put the 1/2 with it. But as we look, again, like if we break this down, this is the base 1 plus base 2. This is our 1/2 out in front. And this is our height of our trapezoid, which is our delta x. Okay, so now to like solve this more easily, I'm gonna pull out that 1/2 in front of everything. And then obviously multiplying by 1 makes this easier too. Okay, so to solve this, we really have e plus 2e squared plus another 2e squared because I factored out the 1/2 plus 3e cubed, another 3e cubed, a 4e to the 4th, another 4e to the 4th, and then lastly, a 5e to the 5th. And then if we go through and just combine our like terms, so we've got 2e squared terms, two 2e squared terms, 2 cubic, or no, that's not cubic, but e cubed terms. And I need to make these videos before lunch when I'm not exhausted. Okay, so if we add that all up, we've got e plus 4e squared plus 6e cubed plus 8e to the 4th plus 5e to the 5th. And that's it. That's our approximation. So then we were asked if this is an underestimate or an overestimate. And remember, with the trapezoidal approximation, we have to go back to the concavity of the function. So I really need to know if g is concave up or down there. So I know I didn't leave myself a lot of room for this. I'm going to find g prime of x in the bottom right. So x, e to the x, using that product rule, derivative of the first times the second is going to just be e to the x plus derivative of the second times the first. And then when we take the second derivative, we get an e to the x plus e to the x plus x e to the x. So our second derivative is 2 e to the x plus x e to the x. And the question is, like, what's the concavity over the entire interval from 1 to 5? And so if I think about that, 1 and 5 are both positive numbers. If I plug those in, I'm going to get all positives. So this function is concave up. And if I think about that, a trapezoidal approximation, we said, is going to be an over approximation on a function that's concave up. So to justify that answer, we need to state that and state that like our approximation or our estimate is an overestimate or over approximation because we used a trapezoidal sum. Gotta say what type of sum. And g is concave up because the second derivative is positive. All right, real fast, let's just look at the graph of this function, which I think I put out here in my no man's land on OneNote. Whoops, that's my keyboard. Okay, so this is the graph of the function g. And we said that is x e to the x. So again, if you look at the trapezoid, it's really hard to see that first one. It looks almost like just a rectangle. But here, I'm just going to show you on a good one. So from 3 to 4, for example, I really could use the ruler tool to make this better. But this is the trapezoid from 3 to 4 that we found, where like this is one of the bases, g of 3, g of 4 gives us the length of the other base. This is our height. And you could see that that trapezoid goes above that curve just a little bit. So we could draw them all on here, but it's kind of pointless once we just see that first one. Okay, so all of these trapezoids are laying down on their height. They're not seated on their base. So in general, I have a lot and a little to say about this last part. So do read the text at the bottom of page 72. In general, there's kind of an analogy that can be drawn between average rate of change and instantaneous rate of change, and then what we're doing now with Riemann sums and what we're going to later do with calculus and mostly in our next unit. So here's the parallel, that what we just did was geometric and we added together a bunch of discrete areas. So we added together a bunch of rectangles or trapezoids in that last example. But we could just think of this generally as rectangles. So the only way that we could get the exact area under the curve is to really have more, but more narrow rectangles. So like instead of having a width that I could even see, like what if I could make this rectangle so thin that it just looked like a line? If I could have a bunch of rectangles that thin, I would get a much better approximation. Like the wider my rectangle and the fewer rectangles I have, the worse my approximation. The more and the more narrow my rectangles, the better my approximation. So when we look at the definition of the definite integral, and I'm not going to go into as much detail as we did when we talked about the definition of the derivative, I'll just tell you that it comes from this summation statement. It comes from a sum. And I want to just kind of break it down. That, that f of x sub I represents the height of the ith rectangle. Delta x represents the width. So this is like the height of the rectangle. Delta x is our width. And then as we add these from I equals 1, so our first rectangle, to our nth rectangle, as we add those up, like without this limit statement, that's just a Riemann sum. That's what we just did. It's this limit statement that tells us that n goes to infinity. So what that means, essentially, I always thought this would be a super nerdy band name, but this means that we have infinite rectangles. It's like a math, like if a bunch of math teachers played in a band together. Infinite rectangles. This tells us we have infinite rectangles, which means that they have to be infinitesimally thin. They have to be so thin that there's infinite rectangles. So thin that we can't even imagine how thin they are. So back when we were talking about the definition of the definite integral at the beginning, and I said dx represents an infinitesimally small width, I'm actually going to color code that to match this, so I'm going to change it. The delta x in the definite integral becomes dx. That represents the width that is so small we can't measure it. F of x represents, well, it's the function, but it's also representing the height of the rectangle or rectangles. And then we use literal rectangles today to approximate that. And in Unit 6, we're going to learn how to find the antiderivative, which is the calculus way to evaluate the definite integral so that we're not always adding rectangles and trapezoids. So that is how these two things relate. And the difference between adding rectangles and using the antiderivative is the difference between geometry and calculus. Just like the difference between average rate of change and instantaneous rate of change, the derivative is the difference between algebra and calculus. All right, so I'm not going to go through this last example for you. We'll just skip that one.